Alrighty, so today we're going to talk about Prandtl's bell-shaped lift distribution. So just to give a little bit of background, so in 1918 and then again in 1920 published, 1921 he published it with NACA. Prandtl published his Tragflugel theory, and I apologize for the pronunciation on that, but that's what you get. He published his results of this lifting line theory, his methods for this lifting line theory. And just to reiterate, that was involved with a section lift distribution equal to 2b rho v infinity squared sum of a sub n sine of n theta from n equals 1 to infinity, where theta can be related to the spanwise coordinate as cosine inverse of -2z over b. And so if you use this lift distribution, you can minimize for induced drag, which results in this series solution of the induced drag being equal to 2 times L over B squared all over pi rho v infinity squared times the summation from n equals 1 to infinity of b sub n squared, where b sub n, we'll define that as the ratio of each of these Fourier coefficients divided by the first coefficient. And we'll also note that lift is equal to 1/2 rho v infinity squared times pi b squared a1. Okay, and so if we take a look at this, we can see, well, the best way to minimize induced drag is to make as many b sub n's go to 0 as possible. Well, we can't make a sub 1 over a sub 1. We can't make that go to 0, otherwise we get rid of our lift. And so what we're going to do is we're going to say, to create this elliptic lift distribution, we're going to say that a sub n is equal to 0 for n greater than 1. And once again, this is for the elliptic lift distribution. And that results in the induced drag equation of 2 of L over B squared over pi rho v infinity squared. Okay. So once again, this is just review. That was what he found using developing his lifting line theory. So now fast forward a little bit. The year is 1933, and Prandtl's taking a look at this, and he's thinking, well, you know, we've got this wing, and it's got some lift distribution. Let's say it's got this elliptic lift distribution, and I'll erase this and move this up above so we have it in mind, but not in the way. So we have some lift distribution that's spread out along the wing like this. And so it's creating this optimized lift distribution that minimizes induced drag. And once again, this is our lift distribution as a function of z. Well, he then thought, you know, most of the weight on this wing structure is carried in the fuselage section, and so we kind of end up with, and I'm trying to draw it a little bit better than I have normally. What if we have this lift distribution that's mostly centered on the fuselage, and then it's got some wing structure outboard? And so he said, well, how do we minimize drag for that case? Mostly because, well, you know, especially in higher loading maneuvers, we're going to have, you know, we're going to increase, oops, excuse me, I got rid of that. Here, I'll write that this is W tilde over Z. Come on. That's not a good ellipse. And so he wanted to look at, well, what if we change this lift distribution over here to more closely match this weight distribution? In other words, what if we try to minimize this wing bending moment? as well as minimizing drag. What will that do for our equations? And so with that in mind, he came up with 4 constraints for his optimization. So he said that first, the wing weight structure distribution as a function of z at each section, so that's what as a function of z means, as a function of z, has to be proportional to, and this is just some proportionality coefficient that we're going to have, to the wing bending moment distribution at the same wing sections. Okay, and once again, this is just a proportionality coefficient. Okay, so a second constraint was that this proportionality coefficient, this ratio of our wing weight structure distribution and our wing bending moment distribution, is not a function of z. So in other words, SB is not a function of z. Of our span-wise coordinate. And I'll try to keep these all on one page. So 3, he decided that his wingspan could vary. Ooh, man. But he required that the gross weight and the ratio of the wing weight structure distribution and the wing bending moment distribution, in other words, this SB value, had to be fixed. Okay, and the fourth constraint he gave was that the wing section bending moment at each section is a function of the lift. And he defined that to be the following function. So we've got m tilde of b of z sub b of z is equal to the integral from z prime equal to z to b over 2 L tilde of L tilde z prime, which is a function of z prime. And then we've got z prime minus z dz prime, where z is greater than or equal to 0. So let me move up a little bit just so they're all on the same screen. So these are the four constraints that he decided had to be true in order for us to develop this lift distribution that would minimize that wing bending moment, but also be optimized for minimum induced drag. So let me just get my notes down here. And what he found was that if he set all of these Bn values to be 0, except for n equal 3, he was able to minimize the induced drag for that while minimizing the the wing bending moment. And he found the Prandtl bell-shaped lift distribution to minimize that bending moment the most, where B3 is -1 over 3. Okay, and that resulted in this section lift distribution, 2 rho v infinity squared b times a1 sine of theta minus 1/3 sine of 3 theta. And that resulted in a minimum induced drag of 8 times L over b squared, that's an 8, all over 3 pi rho v infinity squared. Now, a couple things to note. Prandtl stated that this is not an absolute minimum. But he said that it is the minimum of induced drag for fixed gross lift and fixed moment of inertia of gross lift. Okay, so there's that equation there for the minimum induced drag for a wing, where we are minimizing induced drag as well as minimizing that wing bending moment. And we're going to talk about how to add twists to a wing to make it have this lift distribution. And I'll show this a little bit clearer in the next video, but we have this elliptic lift distribution of some wing, looks like this. Well, the bell-shaped lift distribution is going to look something a little bit more like this. Now that's not very perfect. I'm drawing a little bit too much inboard. That's a little bit better. But that gives you a general idea as to the difference between these two. And once again, we'll talk about it a little bit more in the next video.